Wow, how are you getting service out in the Grand Canyon?
Okay, wait just 1 minute. I hope you hear me. 1 moment. All right, let's see. So you probably know by now, but to unmute yourself temporarily, you hit the space button. So also there's a chat somewhere. Not sure where exactly, but I'll mostly just try to listen. And here's the iPad. Let's see, just start a new one. So I want to make sure, so here's the top, here's the bottom. Okay. Also, there is an option to raise your hand somewhere. I'm not sure what it does exactly, but there is literally a button called raise your hand. It should somehow show me that you want to say something. Okay, let's see. Yep, I'll do the grid. I'll open my notes. Okay, great, one more person. So there was a discussion in the email that some strangers somehow figure out meeting IDs, probably just guess, get in and start streaming porn. So this happens. Close your eyes. I didn't pay enough attention to security for today. Like theoretically, I should have created a waiting room and allow you in one by one, but this makes life harder when someone comes late. So we'll just hope that everything goes smoothly and that our ID won't be guessed. All right. So here are the notes. So first of all, if you have any questions about Wednesday's lecture that apparently went too quick, you can ask them now. Happy to repeat anything. So once again, you press space, unmute yourself. So you hold space, unmute yourself, and ask a question.
Could we record this and so that we also have the videos of this to look back on?
Yes, good idea. So I think I hit the recording button on Canvas. So it is supposed to be recorded. Yes, so when I hit more, it tells me that I can stop recording. So I'm hoping that it is recording right now.
Okay, thank you.
Yeah, but I didn't abandon YouTube. Still want to become famous, so I'll try to upload it somewhere.
I did have a question. It was towards the end. It was in the proof of the family of the theorem of F is AC on AB. That meant that we had that DHF is uniformly summable.
Mm-hmm. Okay.
Like when we got to the part where we were doing like summations less than infinity, like I mean summations less than epsilon. Like I just thought the individuals were less than epsilon. How do we know that the sum is going of them all is going to be less than epsilon?
Okay, so let's see. So we have okay, hang on a second. Now my pencil stopped working. Come on. Okay, second. Let's see. It says connected. Yeah, does work. So okay, so we know. Okay, here it doesn't. Yeah, now it does. Okay, so we know this, that if we integrate DHF from U to V, then it's 1 over H, and I use G, but I'll probably not. So we know this formula, right? This is just change of variables. And so then we set f of t equal to the sum. And I guess what you're asking is, why is this true?
Yes.
Right? Okay, so this is true because f is absolutely continuous. And yeah, just absolutely continuous, because we're looking at these intervals, aj plus t to bj plus t. And although they're all shifted, but their length is the same as length of the intervals aj, bj. So if I sum these lengths, I still get sum of bj minus aj. Correct?
Okay, yeah, I got it.
And this is less than delta. So now I have new family of disjoint intervals. I have this family. They're still disjoint because the original ones were disjoint, and if you shift disjoint intervals by the same number, they remain disjoint. So this is my new family of disjoint intervals with sum of the lengths less than delta. Right? And so because there's sum of the lengths less than delta, it means that sum of the f's is less than epsilon. Because f is
Works because we defined that when it got greater than b, it just stayed the same as f of b.
Right. Mm-hmm. Yep. Yeah, and because f is absolutely continuous, so this arrow is true for any family of intervals, shifted or not shifted. So this proves that f of t is less than epsilon. And then if we look at dh of f over a, so a is the union of intervals, and it's always confusing whether I mean open or half open or closed, but integration doesn't care because the difference between closed and open are in two endpoints, and the integration doesn't care about endpoints. So I'm just now integrating DHF over AJ BJ. And now I take every integral, make this change of variables. Sorry. So this means that I'm having 1 over h. Sorry, no, sorry, I don't need 1 over h here because it's incorporated in DHF. Now I have 1 over h, integral from 0 to h, sum of this minus f of aj plus t. And my point is that this is less than epsilon for every t. And so we get this is less than epsilon. The whole sum is less than epsilon for every t because f was the sum. I'm underlining it right here. So this is exactly f of t. It's less than epsilon for every t. And so we get epsilon times the length of 0h divided by h, which is epsilon. We can put absolute values everywhere. So did it make it slightly more clear?
Yes, thank you.
Okay. So any other questions about last lecture? Okay. I'll upload my notes, by the way, also, but one of the reasons for this confusion with G, which I then changed to capital F last time, was that I used G in my notes for two different things. And confused myself. All right, so our next goal then is to prove the theorem that if f is absolutely continuous again on an interval, then the Newton-Leibniz formula. I can actually write Riemann integral, but I'm going to write Lebesgue. Okay, so with equality here. And we will put together our previous two lemmas. So, okay, so we know that DHF is uniformly summable. So let's call phi n. So this is going to be n, not h. I want a countable sequence. Phi n of x will be d 1 over n f of x. So this is just the limit of f of x plus 1 over n minus f of x divided by 1 over n. By the way, if you have a question, just start talking. So I'm trying to keep track of the grid of names, and if you start talking, like if you start talking, I think even if you're muted, I'll probably see a yellow rectangle around your name, but I'm mostly looking at my iPad, so just start talking. I'll stop.
1 over n is the limit, or is it for a fixed 1 over n?
So n goes to infinity, and 1 over n is in the limit. So I'm replacing h with 1 over n, right? So DHF would be f of x plus h minus f of x divided by h. And now I want to replace h with something small, and if n is an integer, then 1 over n is supposed to be small.
Yes, but dh is not a limit.
Okay, dh, yes, sorry. Good, yeah, that's a great catch. Okay, so not the limit, agreed. The rest stands. Yeah, df is the limit. You're absolutely right. Okay, yeah, so that's the correct formula, and we know that this family is uniformly summable. By the way, so here I don't have any problems with measurability because I know that this fraction is measurable. All right, and so we know that we can rearrange integration with limit. So let's see what do we have. So let's integrate from a to b, phi n dm1. So this is 1 divided by 1 over n, integral from a to b, f of x plus 1 over n minus f of x, dm1, oops, b goes here. Now I will do my change of variables again. And then I'll remind you that we've done this once when we proved the same thing but with an inequality for an increasing function. So we had absolutely the same formula. We did the change of variables, and then we figured out that what it's equal to is this. So we have the integral from a plus 1 over n to b plus 1 over n f dm1 minus the integral from a to b f dm1. Then a lot of things cancel out, and we recall that f of b plus whatever plus star is the same as f of b for a positive star. So eventually, and you see that these intervals overlap a lot, so almost everything cancels out. So what's going to be left is the integral from b to b plus h minus the integral from a to a plus h. Now the integral and 1 over n instead of h. Now this first integral is easy because whenever we're bigger than b, f is equal to f of b. So we get 1 divided by 1 over n, 1 over n times f of b. And this second integral, last time we estimated it. So last time we just said that because f is increasing, then f is bigger than f of a, so minus the integral is smaller than f of a. Now I don't want to estimate because now I need to prove an equality. Okay, so this 1 over n and this n cancels out. So what I have is f of b, which makes me really happy, minus this. Okay, and now I want to pass the limit as n goes to infinity. So let's scroll back. So I have this is equal to this. So when I pass to the limit right here, I can interchange it with the integral, and limit of phi n is the derivative of f almost everywhere. Whenever the derivative exists, limit of phi n is derivative of f. So here, I feel really comfortable passing to the limit because phi n's are uniformly summable, so I can bring the limit under the integral, and I win here. So what's left to do is to prove that the limit, and I'll replace n by h again. The only reason I wanted a countable sequence is to pass the limit here. So I wanted the countable sequence somewhere here. Here it can be relaxed. So I just want to prove this. That this is equal to f of a. Now, but f was only increasing. We had no way to do this because, well, this definitely requires some kind of continuity. So if f is just increasing, that it's almost always continuous, but it can be discontinuous at A. Now here f is absolutely continuous, so we have this extra continuity and we can prove this. Well, why is this true? So I'll leave the details as an exercise, but the way to do it is just to write absolute value of 1 over h integral from a to a plus h f minus f of a. And now I'll write f of a as the integral from a to a plus h. Okay, I'm going to write it and then I'll wait for a couple of seconds for you to look at it. So, so when I integrate f of x, well, I get this. And when I integrate f of a is a constant. So I integrate a constant over this interval, I get this constant times the length of the interval. And then I also divide it by h. So h cancels out and I just get f of a. And now I'll bring the absolute value inside. Oops. Absolute value of f of x minus f of a. And this goes to 0 because I can, for example, write that it's, so there are several ways to do this. One way to do it is to estimate this difference by its supremum over this interval. And when I estimate it by the supremum, I factor it out, then I get the length of the interval, which is h. It cancels out with this h. So 1 over h times the integral is less or equal than the supremum of f of x minus f of a when x is an a plus h. And now because f is continuous, so it's uniformly continuous, you can, yeah, I actually don't even need uniformity. Because f is continuous, this goes to 0. So that's the only detail I leave to you. But it's, well, it's kind of intuitive because I have f of x minus f of a, and the length of the interval here goes to 0. So f of x must get close to f of a because f is continuous. Okay, so this goes to 0. This implies that 1 over h integral a to a plus h f dm1 converges to f of a as h goes to 0. And now we're done. Why are we done? Because once again, we pass the limit right here. And we interchange it with the integral. So the limit goes right here. And the limit of phi n is the derivative of f. And then I have only equalities here. I have equality here, equality here, equality here, equality here, and equality here. I never estimated anything. And then I pass the limit here. And by the final goal, this second term goes to f of a. So we're done after taking the limit as n goes to infinity. Okay, so that's a very powerful result. So in calculus, a while ago, you learned that this Newton-Leibniz formula holds when f is differentiable, and now it holds in a slightly relaxed situation when f is not always differentiable, but most of the times differentiable plus supercontinuous. So this implies a very important corollary that if f is absolutely continuous on the same interval, So this is if and only if there exists a summable G with this. So, yeah, so f has an antiderivative in this sense. Now, one arrow is done. So this arrow that if f is AC, so AC implies the existence of G, is now easy because just take G equals to f prime. And then we know that the integral of f prime from a to x is f of x minus f of a. F of a cancels out, and we get f of x. So we need to prove it the other way around. What if such a G exists? Well, so if such a G exists and it is summable, we know that this implies that absolute value of G is summable. And by the continuity of the integral, we know that for every epsilon there exists a delta such that measure of A is less than delta implies that the integral of G, of absolute value of G over A is less than epsilon. So this used to be called absolute continuity of the integral. Okay, so now let's write what does it mean that, well, not what does it mean, what do we want to get to show that f is absolutely continuous? Well, we want to take a family of disjoint intervals with total length less than delta and estimate this sum. Okay, so we know that each individual difference is an integral. Bj, or I'm not sure, I might have used open here, but doesn't really matter. Okay, now I'll bring the absolute value inside. That's my only hope. I cannot bring the absolute value outside of the sum because I'll get an estimate in the wrong direction. So I'll bring the absolute value inside. And now this summation acts beautifully because these intervals are disjoint, or at least their interiors are disjoint. So again, everything is done up to the endpoints, but I have finitely many of them, so endpoints don't really matter. I can be careful this once. I can write that this integral is equal to this integral. And now, because I'm summing up integrals over disjoint intervals, I can just integrate over the union. Okay, everybody clear? I cannot see most of your sad faces, so
So when we made that first substitution in the summation from G, we were able to do that because f of x equals f of a plus the integral, and the f of a's would.
Yes. Yeah. So so this is something I might have skipped. So if this holds, then this holds for any a inside the intervals, right? Because now we can say that this holds for x equal to bj. It also holds for x equal to aj. And if you subtract, then f of a cancels out. And you're subtracting an integral from a to bj minus the integral from a to aj. And this is the same as the integral from aj to bj. if this is what you were asking. Was it?
Yeah, thank you.
Yeah, so we're using this formula. So we're using this formula for x equal to bj, and then x equal to aj, and then subtracting them. And everything is finite, by the way. I have no problem subtracting because f is continuous, so it's bounded, and g is summable, so all the integrals are finite. So when I subtract, like, I have no issues with infinity minus infinity. All right, anything else? Okay, so we will now set A to be equal to this union. And we know that the measure of A is less than delta because from the very beginning, we assume that these are disjoint intervals of total length less than delta. And by this line, it implies that the integral of g, absolute value of g, over A is less than epsilon. And this is exactly what we wanted. So let's look at this proof again. So what we do is we start with this family of disjoint intervals of small total length. And we estimate the oscillation of f by this, and this is less than epsilon. So this proves that the sum from 1 to n f of bj minus f of aj is less than epsilon whenever this family is disjoint with total length less than delta. So I just want to call your attention to the fact that this disjointness assumption is very important. Yeah, so we use it in every proof. If you look at every proof, you'll see that we use it once or more than once. Here, for example, we used it in this equality. If they were not disjoint, we would get the wrong estimate, we would get bigger or equal here. So disjointness is important. Okay, so here's a corollary. So let's go back to increasing functions. So if f is increasing, not continuous anymore, on AB, so then we already know that if we integrate the derivative, the integral is less or equal than f of b minus f of a. So what can we say if it's equal? So how often does this formula actually hold? Well, it turns out that this formula holds if and only if f is absolutely continuous. So if f is not absolutely continuous, then we get strictly less. Okay, so remark is that we know less or equal right here. So if f, well, after we prove the corollary, we will know that if f is not AC, then we have strictly less. Have a strictly less sign there. All right, so let's prove the corollary. Well, one error is clear, so we already know this. This was the first thing we proved today. We only need to prove that if this holds, then f is actually absolutely continuous. I also want to call your attention to the fact that this is not something that that has a quantifier right here. Okay, it's only for the endpoints. It's not that I'm saying that if this is true for any b, so or for any x. I'm saying that it must be true only for the endpoints. And then f is absolutely continuous everywhere, and so it's true for anything inside the interval. Okay, so let's set phi of x equal to f of a minus integral from a to x plus integral from a to x f prime dm1. So we already know that phi is absolutely continuous. Okay, so f is increasing implies that f prime is summable. So summability is because we have less or equal here. Less or equal is enough for summability. So f is summable. And by the previous theorem, this implies that phi is absolutely continuous. Okay, I can scroll back the previous theorem. The previous theorem says that if we write this formula for a summable G, then f is absolutely continuous. So phi is absolutely continuous, and the obvious goal is to prove that phi of x is equal to f of x. Even if we do this almost everywhere, we will win, because we have, okay, you know what, maybe no. So I'll try to prove this everywhere. Okay, so how are we going to do this? We'll do a trick. You know what, I'll probably go to the next page. So we will write the integral from a to x f prime, and it is less or equal than, don't need parentheses here, than f of x minus f of a. Integral from x to b of f prime is also less or equal, but then f of b minus f of a. Minus f of x, sorry. F of b minus f of x. Right? So this is something we proved, I think, in our first virtual lecture, let's say. That for an increasing function, or maybe in class, start forgetting things. But anyway, for an increasing function, we have a less or equal here and here. All right, so now I want to send everything to the left-hand side, and I'll write this integral from a to x f prime dm1 minus this is less or equal to 0. Yep. And now I'll sum these inequalities together, but I'll try to do it wisely. So when I sum them, what do I get? I get integral from a to x f, that's a very ugly x, from a to x f prime dm1 minus f of x plus f of a plus integral from x to b f prime dm1 minus f of b plus f of x less or equal to 0. All right, now I want to recall what's phi. So phi is okay, hang on a second. So I want to prove that I have a 0 here. I want to prove that I have a 0 here. So so do I need to do anything? Yeah, great. So f of x cancels out. Yep, I'm fine. F of x cancels out. Now, yeah, I can actually do this. So this and this is equal to phi of x. And now this and this is equal to minus 5b, minus 5x. So what I get is the true statement. Okay, but now let's look back here and assume that one of these inequalities was strict. So assume that we had, for example, a less here instead of less or equal. So what if we had strictly less here? Well, we would sum them up and would have strictly less here, then would have strictly less here, and then would have strictly less here, which is wrong. So 0 is not strictly less than 0. So what I'm trying to say is that if we have a true inequality here, then so what I'm saying is that if we have an equality here, then we must have an equality here, an equality here, and an equality here, and an equality here. Because once again, if one of these were strictly less, then this would be strictly less, this would be strictly less, and this would be strictly less. That is wrong. Okay, I pointed to the inequalities I meant, but you obviously cannot see what I'm pointing to. So if one of these are strictly less, then this is strictly less, then this is strictly less, and then this is strictly less, which is wrong. So what we actually achieved here is that we had equality both here and there, but I probably need only one. Yes. And this is true for every x. So this implies that f is absolutely continuous. This implies that f is absolutely continuous because of this. Because of this here. Because f prime is summable. F prime is summable, and we get that f of x is f of a plus the integral of f prime. And I put the limits in the wrong place again. Here we go. Okay, any questions about that or about anything else? So every step in this proof is easy, but proofs here just got long, like every single one is long. So,
Professor, I have a question.
yep.
For the phi definition is equal to fa plus the here
Mm-hmm.
fa plus the integral. So why when f prime is summable, phi is absolutely continuous?
So f prime summable implies that phi is absolutely continuous by this theorem.
Yes, that's fx equal to fa, but that in the phi is phi x equal to fa. So
That's fine. Okay, I see what you mean. So you're saying that I need to compare phi and f. Well, let's plug x equal to a here. We got that phi of a is equal to f of a. If we plug x equal to a, then this becomes 0. We're just integrating from a to a.
okay. Okay.
So phi of a is equal to f of a. And yeah, good question, but no problem here. And in fact, if you look at this proof, not at the statement, but at the proof, you'll see that this constant doesn't really matter. It just cancels out because we're taking differences here. So whatever constant I write instead of f of a, it will cancel out. But that's a reasonable concern. Okay, and so now I'll state the theorem and I'll try to not start proving it, but you'll go for the weekend knowing the most important theorem in this chapter. So we now assume f is only summable. So we don't assume it's increasing or continuous or differentiable or anything. So summable on AB. Then for almost every x in the open interval, we have this, that if we integrate from a to x f dm1 and then differentiate it with respect to x, then we get f of x. So this is also something we know from calculus for decent functions. So if f is continuous, so I encourage all of you to try to prove it for continuous f. So for continuous f, it's like classical. So for continuous f, you don't need Lebesgue integration to prove anything. You just estimate like we did when we integrated f from a to a plus h. But when f is only summable, this actually becomes a hard and a very important result, and this is called the Lebesgue differentiation theorem. Lebesgue differentiation theorem. Now, many textbooks start with this theorem. So it's possible to prove it without going into absolutely continuous functions. With a completely different approach. It still requires some kind of covering lemma, slightly easier than Vitali. And then it requires something that's called maximal function. So if you look at Rudin, for example, or I think even Folland does that. So almost nobody proves this result going through the increasing functions. Only Royden does, and this is an exceptional case when Royden does a great job, because on the way we acquired many other important results. So taking this route is a little bit longer, but we learn lots of things that Rudin, for example, just simply skips. Okay, and so we will prove this next time. Again, I encourage you to do this for a continuous function, and then see how nothing works for a summable function. And so next time we'll start with this. Okay, so any last minute questions? 5 minutes questions. Okay, so if no, then see you on Monday. So I hope this got recorded and then I'll upload it on YouTube. Well, to me it went well. Like still Classroom is better because I could see your faces and try to guess when I'm going too fast, but probably it's still an improvement compared to live streaming on YouTube. So I'll create one more for Monday, and I guess I'll see you there. Yes. Okay.
Yeah, I agree. I think this was much better.
Thank you.
Because I think this way we can do both, because we can still go back and see the video.
Okay, now you disappeared.
Videos again later
Uh-huh.
on YouTube if we're kind of lost in a specific section.
Mm-hmm. Okay,
Mhm.
so okay, maybe it's not you, maybe it's me who disappeared. So yeah, so if you, I'll still be happy to answer questions about the mess on YouTube. So I'll try to ask if you have any questions, like in the beginning of every virtual lesson. I probably just watch too many gaming streams that I'm super comfortable with all this live streaming stuff. Okay, so then I'll see you on Monday and hope you have a good social isolated weekend. So bye-bye.
Thank you, you too.
Mhm.
Bye.
Thank you.
Yep.